Okay, the third and final method I want to discuss is called instrumental variables. Remember when we introduced notation for causal inference, we had a variable z. Well, that's called an instrument, and that's what we're going to use in this final method of estimation for causal inference. And IV, or instrumental variables, is appropriate when the conditional independence assumption fails, completely fails. So the presence of confounding is such that we know that there's not unconditional independence, but we don't have sufficient data to represent X in order to invoke a conditional independence assumption. And if that's the case, then there's nothing we can do to achieve identification via direct covariate adjustment because we don't have available data. So OR and PS methods are out. Now, we're going to look at instrumental variables, which in the context of a linear model, that's the setting we're going to look at. IV is often used in this context. It can be used in non-Gaussian models, but we're going to stick with the linear form because it's easy to derive analytical results and ones that compare directly with previous lectures and with the material we covered under identification of a linear model earlier. So this is the multiple linear regression model we're going to assume. And again, we're going to use bold notation because just to keep things consistent with our work on the linear model previously. We want to estimate parameter vector beta, but the conditional independence assumption has failed due to omitted variable bias. And so in order to do something about that, we're going to use instrumental variables. Now, there's an identification problem in this model due to confounding, as I've just said. And this arises in the linear setting where the error term is not independent of the covariate. So the error term, U, is not independent of covariate vector D, and this violates Gauss-Markov condition 3. In the language of instrumental variables, we say that there's an endogeneity problem. And the logic underpinning instrumental variables is that we're going to directly remove this correlation problem by the model by introducing a set of observable variables known as instruments, which we're going to denote by bold Z. So what is an instrument? Well, an instrument is a special type of covariate, one that's going to help us solve the identification problem that has two, or must have two, unique properties. First of all, it must be what's called exogenous, or it must satisfy the exclusion restriction. So the instrument must be uncorrelated with the error in the non-identified model. So this model here has error U. There's an endogeneity problem because D is correlated with U. Well, the instrument must not be correlated with U. So that assumption must hold the exclusion restriction. That means the instrument is we call exogenous, and it would never feature in the non-identified model. So the instrument would never be an explanatory variable in the model for Y. Secondly, the instrument must be what's called relevant. That is, the instrument must be correlated with the endogenous explanatory variables, or the instruments actually, which we call D here, conditionally on the other covariates. So this is a DAG that demonstrates the relationships that are embedded in an instrumental variable model that are required for identification. Changes in Z are associated with changes in D, that is, Z is correlated with D, but they don't lead to any changes in Y other than through the path that leads from D. So Z is causally associated with D, but it's definitely not associated with U, which appears as a term of Y. And Z would therefore not appear in the regression model for D. So it's relevant, correlated with D, but it's exogenous because it's not correlated with Y other than through D, and it's certainly not correlated with the error term. So how does an instrument, a valid instrument that satisfies these two conditions of exogeneity and relevance help? Well, under instrumental variables, we achieve identification by using the instruments to enforce orthogonality between the error term and the instrument transformed design matrix. And to see how this works and achieve identification, we can do it very simply if we assume that the dimensionality of the covariate vector and the matrix of instruments is the same, so they're both n by k. And if that's the case, then we can demonstrate identification by simply multiplying the linear model by the transpose of Z. So we multiply this linear model here with the transpose of Z. This gives us this expression. We take expectations of both sides of this expression and use our exclusion restriction. That reduces to this expression here, which gives us an expression in beta in observable quantities. There's no error term. The error term's been taken out by the fact that the exclusion restriction holds. So we've managed to get rid of this part here. But because Z is correlated with D, it's still there, and Z is an observable variable. So these expectations then can be consistently estimated using observed data. So beta is identified using the instrumental variables. And there's a proof slide here that goes into a little bit more detail. I won't go through it here because you can do it in your own time. It just adds a little bit about consistency of IV, and it is consistent in the probability limit. In the explanation of instrumental variables that I've covered so far, the simple explanation in the previous slide, we assume that the dimension of Z is equivalent to the dimension of D, but that's not a requirement. That doesn't have to happen for IV to work. There is an order condition which requires that the number of instruments is at least as big as the number of endogenous covariates. So given this expression here. And in fact, exogenous covariates can act as instruments in their own right because they satisfy the two IV validity conditions. So for instrumental variables, all we need to do is find as many or more valid instruments as there are endogenous covariates. Now, when the number of instruments is equal to the number of covariates, the model is said to be just identified. When L is greater than K, the model is said to be over-identified. And the IV estimator that we looked at above, not estimator, but this condition here, required that L equals K. But that doesn't have to happen. So in the over-identified setting, we could simply discard some instruments, but that would result in a loss of efficiency. So instead, in both the just identified and over-identified model, instrumental variables is usually implemented via what's called two-stage least squares. And the process is defined in this slide here. So for a regression model that we've been looking at in this part of the lecture, with an endogeneity problem, failing Gauss-Markov condition 3, and given instruments Z, which are valid and which have the rank condition, they satisfy the order condition, then two-stage least squares proceeds as follows. First, we regress each column of the instrument matrix, each column of the design matrix on the instrument matrix, and we save the predicted values. So this is the predicted value here. That, of course, is the hat matrix that we've talked about previously in the course. The hat matrix that's we recover from regressing D on Z. And then we regress Y on the fitted values from the first stage to get our IV estimates of beta. And with a bit of matrix algebra, you can write the two-stage least squares estimator in this form here, expanding the Y so that it's written in terms of the true value of beta. We get this expression here, where the second term in brackets is going to disappear due to the exclusion restriction. So due to the independence between Z and U. So that's the beauty of instrumental variables. We just regress each column of the design matrix, each endogenous D on the instrument matrix, save the fitted values, plug them into a second stage regression, and we get the IV estimator of beta. And we can derive asymptotic results. We won't do it here by applying a law of large number to these sample moments, so that would be straightforward. There's a few notes here about just some points regarding the two-stage least squares estimator. First is that it can be interpreted as OLS in this form here. That's just telling us that that's essentially an OLS regression on the fitted values. In the just identified case, this expression simplifies to the one that we saw right at the start of the lecture, this one here. And the final point to make is that when you're estimating IV yourself, you don't have to do both stages because most regression packages will do this process automatically. So that's instrumental variables. When the conditional independence assumption fails, it can estimate average treatment effects for us. However, I want to make a few points here. First of all, the IV estimator does estimate average treatment effects, but the average depends on the choice of instruments. And this is actually important because it means that instrumental variables doesn't estimate a population average treatment effect, it actually estimates a local average treatment effect. So refer to it as the local average treatment effect, the LATE, and it is in general not the same as the population ATE, which, as we know, we would achieve by integrating over the distribution of covariates, but we don't have those covariates, so we introduce random variable Z, but the model is only valid for the subsample which comply with the requirements on Z. So it cannot be easily extrapolated to a population. The ATA is dependent on Z, and that's why we call it local rather than population. Some other points worth mentioning on instrumental variables. It can identify these local causal effects for us in the presence of endogenous covariates, in the presence due to the failure of the CIA, but actually in practice, exogenous and relevant instruments can be hard to find. And even slight violation of the exclusion restriction can induce large inconsistencies in parameter estimates. So if the instruments don't satisfy this restriction, actually the cure can be worse than the disease, and I'll demonstrate that in a minute when we look at a simulation. Secondly, if instruments are only weakly correlated with the covariates, so if they're not highly relevant, the second condition, then IV estimates will be biased in the direction of OLS. And what makes these, these caveats on IV important to take on board is that diagnostic statistics on instruments are available, but they do not provide a foolproof means of detecting whether instruments are valid or not. So it's risky. We use instrumental variables in the hope that we're curing a problem, but if the instruments don't satisfy the conditions, they can actually make things worse, and it's very hard to determine whether they've made things worse or not, given the diagnostic statistics from an IV model. Okay, so let's introduce a final example to demonstrate instrumental variables. Again, using simulation for the same reason we did previously, because we need to be able to establish that causality is genuinely being uncovered by the model, so we need to control the data generating process. In this example, we're going to imagine that the objective of our inference is to estimate the effect that urban density has on automobile use, and that's actually an example that's been looked at in the literature where IV has been used. So the question is, does the density of development affect the decision on car travel, and particularly on whether to own and use, how much to use a car? But there's a causal inference problem, because due to self-selection, there are unobserved confounders that simultaneously determine urban form and automobile use. So think about it, people who do not like driving live in places that do not require cars. So they self-select into neighbourhoods where they don't require a car, or if you like driving, you self-select into a neighbourhood where you can use your car because you enjoy doing so. So there's a reverse causality and confounding going on here, which is where instruments are very useful, because we don't observe these self-selection factors. We have an instrument Z that measures, let's say, some underlying geological characteristics which are correlated with density but not with automobile use. So this is the data generating process we've specified. These are our covariates that we don't observe. This is our instrument. This is the model for the treatment, and you can see that the instrument appears here, so it's relevant. That is, it has a tangible effect on assignment to treatment. This is the outcome regression. The instrument does not appear in this model, which is good because that satisfies the exclusion restriction. These are the parameters that we've set in the model, and the true causal effect that we're interested in, beta D, this parameter here, is equal to -1. That's the value we've set. So increasing urban density tends to reduce car use, and that's of course what we would expect. So we're going to simulate the following estimators. First, for the purposes of comparison, we're going to simulate two outcome regression estimators. That is, one based on a correctly specified model where the unobserved covariates are available, they're observed in this model, so we can put them in, and that we know from previous simulations is going to give us a good answer. We're then going to look at a naive, incorrectly specified outcome regression model where the covariates X are excluded, and we know from previous results that's going to give us a bad answer, it's going to give us a bias estimate. Finally, we look at two IV estimators. One, two-stage least squares using a valid instrument that satisfies the two conditions, and we plug it into the second stage regression. And secondly, also two-stage least squares, but this time using an invalid instrument that has correlation with the endogenous covariate, the treatment D, and according to theory, that should give us a bad answer. So again, each simulation based on 1,000 runs on generated data sets of size 1,000. This is the average of beta we obtained from the 1,000 runs. This is the empirical variance, in other words, the variance of the sampling distribution, and this is the MSE. So, the correct outcome regression model, the one that includes X in the regression, obtains an unbiased estimate of beta D, -1, perfect, just as we saw previously. So, if you can put covariates in a model, you should do so. But sometimes we can't, and when we can't, if we just exclude them and estimate the naive model and don't make any adjustment for confounding or simultaneity, that leads to a poor estimate of beta D. It's biased here, as you can see, -0.8 is the expected estimate. The IV model estimated with two-stage least squares using a valid instrument. This IV does the job. It does what it does, what we wanted it to do. It removes the error correlation between D and U via Z. And it essentially nullifies the effect of confounding bias and consequently produces a consistent estimate of beta D. And you can see it here. So it does just as good a job as the outcome regression model using the valid instrument Z. However, when we use an invalid instrument, as in IV2, in this case an instrument that fails the exclusion restriction, this produces an average treatment effect estimate with larger bias than the naive OR model. So it gets it worse than not dealing with confounding itself. And this is this problem that I mentioned earlier, where use of invalid instruments can give a cure that is worse than the disease. So you have to be careful.